Good morning, everyone. We're going to pick back up here in chapter 4. So just give a timeline of where we're at. So we're going to probably get through most of our chapter 4 slides, probably Wednesday's lecture, and then we'll have the remaining time Wednesday, Friday for some in-class review. And then looking into next week, next Monday morning, I'll be here 7:15 for the review prior to next Tuesday's midterm. So if you want to come in early, I'll also record it as usual. But I'll be here 7:15 next Monday, and then test is next Tuesday over chapters 3 and 4. The test is not cumulative, so we're just focusing on the 2 new chapters that we've covered since midterm 1. Okay, so getting back into acid and base reactions. And so the acid-base neutralization reaction is that we form a salt plus water. So you might remember this from last time. You have an acid and a base react together. The product is a salt, which is another way of just saying an ionic compound, and then plus water. And what we need to have is we just need either the acid or the base to be strong in order for this reaction to take place. And last time we saw a monoprotic strong acid, HCl I think it was, and a monoprotic weak base, NaOH, reacting together to form NaCl and water. And we also did it with a weak acid. So we had HF, if you recall from last time, we had HF plus NaOH or KOH, and that was forming the same type of product, KF plus water. And we were getting these reactions going to completion here. So if you're thinking, do we get an equilibrium or full reaction? We just need one of these two, if not both of them, to be strong. And so KOH is a strong base, so that certainly helps this reaction take place. So the hydroxide ion is what makes KOH be the strong base in solution. So KOH in water is really potassium ion and hydroxide ion. The hydroxide ion is capable of pulling those acidic hydrogen atoms off of a molecule. So H3PO4 doesn't release them into water. So H3PO4 is a weak acid, meaning it's going to keep most of those H plus ions intact, only release a few of them into water, but the hydroxide ion is going to be capable of pulling them off and reacting with the phosphoric acid. So we should be able to get all the way to that anion that we learned how to name back from nomenclature. So we should be able to get to the salt or ionic compound that goes all the way to K3PO4, water soluble because we have potassium ion here. And so we get all the way to the phosphate ion, meaning the hydroxide ion is pulling all 3 of these hydrogens off of phosphoric acid. And so we end up getting water that forms here. Water is our solvent, we just write that as a liquid. And so then how many water molecules we get? Well, we know there should be 3 KOHs to balance the potassiums for the reaction. So there's 3 Ks on both sides. That hopefully shows that you have 3 OH minus ions. Each one of those OH minus ions is going to pull an H plus ion off of phosphoric acid. So that gives us 3 waters that form. And so you can think here I have 3 H pluses to pull off of phosphate, and I have 3 OH minus ions to then form a water molecule off of each of those pairs. Now, when we start thinking of can you write a net ionic reaction for what's going on here, that's really just trying to picture, well, what's the actual net change for this reaction? So when I start thinking, can I break apart these substances into ions? The question is, are these strong electrolytes? Is phosphoric acid a strong electrolyte? The answer is no. This is a weak acid, weak electrolyte. And so we leave that, and the ionic equation is H3PO4 aqueous. So we don't break apart that into 3H plus and phosphate ion. So the question of when you start ionizing to get towards what we write as the net change, or the net ionic reaction, you can only ionize the things that would ionize in pure water by itself. So the thought should be strong electrolytes completely dissociate, but weak electrolytes do not fully dissociate. So we leave that mostly as H3PO4, or the solution is mostly H3PO4, so we leave that as that in the balance reaction here. And so then my KOH is a strong electrolyte, so I break that apart into my 3K plus my 3 OH minus ions. So the KOH solution is really potassium ions and hydroxide ions, not really KOH stuck together. Like H3PO4, those atoms are really still stuck together. And then when the reaction takes place, the hydroxide ions will find the H plus ions, bump into them, pull them off. The organic lingo, if you've ever seen this, is attack. The hydroxide ions go and attack the charge on the H3PO4 molecules. And so then we're forming the K3PO4, so that's 3 K plus ions and a PO4 3 minus ion. And a lot of times with the ions, I don't necessarily write AQ, but if you see a plus charged ion, of course, it's surrounded and dissolved in water as an AQ. And then we get our 3 waters. Water is not an electrolyte, so we leave water intact as H2O liquid. So water is not a strong electrolyte. So the thought is I ionize in my equation the strong electrolytes. Everything else, weak electrolytes or non-electrolytes, I leave intact in their molecular form. And so then what I can do is I can cancel out anything that happens to be the same on both sides. Now, this doesn't mean that the potassium ion disappears from the equation or the problem or the solution. It just means it's not part of the net change. And so the net change, the net ionic equation here would be H3PO4, AQ plus OH minus, 3 of them, AQ, forms PO4, 3 minus AQ, plus 3 water. Okay. Again, I don't know why my screen has a tendency of just spontaneously erasing, but we got it back here. Just trying to write the H2O liquid in. So H3PO4, AQ, plus 3 OH minus ions goes to phosphate ion plus 3 waters. And so this is the net ionic equation here. This is what lets you see the net reaction. So the net reaction, the net ionic equation is just letting us see, is there a net change? If you recall, remember when we started talking about metathesis reactions, we had the example of needing to form a precipitate in that reaction. If you didn't form a precipitate, then you just had ions on the left side, the exact same ions on the right side. There was no net change. And so the process of trying to find the net ionic equation is just a way to try to make sure there is an actual chemical reaction taking place. And so here we would have a net reaction taking place because we get to, a net change, there being a difference on the left versus the right side. And so that's the process for this reaction of finding the net ionic equation. Now, what about having something like this strong acid, and then ammonia is our prototypical example of a weak base, partially ionizes in water to ammonium and hydroxide ion, but not completely. And so when we have HCl and NH3 react together, the product here that we get actually won't involve water, just because what we're going to do is have the base take the H plus ion, so we're going to form ammonium cation, and then we're going to form chloride ion as the counterpart. And ammonium chloride would be a water-soluble ionic compound. Now, ammonium is the weird example where you get an ionic compound that doesn't contain a metal ion. So if we were to write this as NH4Cl AQ, we could write it in the molecular form, but it's really going to be ionized because ammonium's an ion, exists as the NH4 plus ion in that compound, chloride's an ion, and water, this would be subject to the solubility chart. Ammonium is an ion we consider kind of like our metal cation. So this would be a water-soluble compound, so we'd have our plus and minus charged ions. And so this case here, we'd have the full reaction. Now, the reason why I want to stress this is as long as you have a weak acid or a weak base, or both, as long as you have one of the two being strong in terms of either a strong acid or a strong base, you're going to get a 100% reaction take place. And it's going to be generally a pretty quick reaction that takes place if you were to do this in a lab setting. I would like to differentiate this since we talk a little bit about equilibrium and how the weak acids and weak bases only partially react. You get full reaction here provided at least one of the two substances, the acid or the bases, is strong. If they're both strong, that's even better. You're definitely going to get the full reaction to take place. And if you're wondering what happens if you mix a weak base and a weak acid, a very interesting problem emerges that we don't have the tools yet to solve. You'll see that again in chapter 16 come up as an issue. It really comes down to, is the acid a stronger acid or is the base a stronger base of the two? But it's not a question we can handle right now. So if you have a weak acid, weak base, we actually do end up still with an equilibrium that we're not going to talk about. So you won't see an example like of HF reacting with ammonia. That would be kind of a tricky problem for us to solve here, just to give you an idea that we're just looking at strong acids with strong or weak bases, or a weak acid with a strong base. Okay, so let's look at a couple other reactions here. So when we have acid-base reactions take place, we could have something like carbonate ion here, 2- charged ion. We can have our HCl solution. And here, the H plus ion and the carbonate can exchange with each other, and we'll end up forming H2CO3. But carbonic acid is actually very reactive in water and doesn't actually exist in water because it would rapidly decompose into CO2 into water. And interestingly, that doesn't really make it a strong acid because we're not getting ionic products, we're getting two molecules that forms. So we just have an unstable molecule in the form of carbonic acid. So carbonic acid, if we form it, just rapidly decomposes the CO2. Now this makes things that has carbonate useful for like cooking purposes. This is how you can get the rise in flour, is by having something like either carbonate ion or HCO3 minus that can then react with acids in the mixture and then produce air bubbles as a result. And so if you have sodium hydrogen carbonate, a key ingredient in baking soda, you can get this rise action. We showed here reacting with HBr. You would get HCO3 minus plus the H plus going to H2CO3, and then that rapidly decomposing to CO2 and water. So we're getting CO2 to form as a gas here, and then our byproduct, of course, is just NaBr, our salt, and then calcium chloride for the first example. We have the calcium ion and the chloride left over to kind of be the salt or the IC that forms to balance out the reaction. And then an interesting reaction takes place with sulfides, where you can have sulfides and H plus ions react, and then we get H2S, hydrogen sulfide, that then bubbles away from the solution. One of the lessons here is that what drives these reactions to take place, what allows a reaction to take place to like 100% yield, is the ability to form something that doesn't go back to the reactants. You know, so like anytime you can have a reaction where if you form something that becomes kind of like a sink, and then once you form it, it doesn't revert back to the reactants, and you have a reaction take place very quickly and towards 100% towards the product side. And so the things that help drive a reaction take place are forming a solid that's insoluble because it just removes itself from the mixture. So solid formation is one way to drive a metathesis reaction. Another way is to form water in an acid-base reaction because that forms a substance that doesn't break back apart into H plus and OH minus ions. So forming water is another way to drive a metathesis reaction, such as acid-base reactions. But we also see forming a gas would be helpful because if you form a gas, it floats away and it can't reform and go back to the reactant side. So we can have solid formation, we can have non-electrolyte formation, or we see here you can have gas formation to help drive these types of metathesis or exchange reactions to taking place. And so with that kind of wraps up the first half of chapter 4. So the first half of chapter 4 is trying to understand some of the properties of solutions that have ions in them, the electrolytic nature of those solutions. So talking a lot about ionic compounds and the process and how they dissolve. If they dissolve, they ionize completely. If they don't dissolve, they're just stuck together as the solid form. And then we have the ability of acids to act as strong electrolytes or weak electrolytes, depending on the nature of the acid. And then we have the presence of weak bases that can weakly react with water to produce some ions. And we have strong bases that are already, if you recall, categorized as being water-soluble ionic compounds like calcium hydroxide, sodium hydroxide, that produce that OH minus ion. So the second half of chapter 4, we'll get into, first we'll see some examples here today in the notes of oxidation reduction reactions where we have those types of reactions taking place where we have the exchange of electrons. So we'll talk about that type of reaction next, and then we will have the quantification of the aspects of these reactions, talking about solubility units, the molarity unit, and getting into some stoichiometry problems here in the second half of chapter 4. So let's actually start this, let's take a detour and do a stoichiometry question. So this is kind of towards the end of the notes. If you're looking for this, this is in like the last 5 pages of the slides for chapter 4. We have sodium solid, CO2 reacting to form NaCl solid. You might want to think about writing and balancing the equation for that reaction. And we're asked to determine what the mass of product is that forms from the reaction of these quantities of reactant. So I wonder if you guys can take 2 minutes or so and see if you can come up with the answer to the question. All right, so let's take a look at this one. So one of the things that we often will have to do in a problem like this is be able to write the balance reaction and make sure we get the coefficients right. Because if we neglect the coefficients, we may not consider the mole ratios here, that we need 2 moles of sodium to react with 1 mole of Cl2 to give us 2 moles of NaCl. So that puts 2 sodiums on both sides, that puts 2 chlorines on both sides. So we really need to make sure we have these coefficients here of 2 to 1 to 2 for this reaction. And then there's a couple different ways that you may have thought to solve the problem. All of them might lead you towards the right answer. So if you took a different route, that's fine. But I was thinking probably the fastest way to solve this problem would be to consume all the sodium and say, if I took the 23 grams of sodium, I convert it to moles, and then say for every 2 moles of sodium that reacts with as much chlorine as it takes, we'll get 2 moles of NaCl. And so this step here kind of requires me to think about this reaction. So it's just saying for every 2 moles of sodium that react with as much Cl2 as it takes, we get 2 moles of NaCl. And then just converting to grams of product, that would be 58.5 grams of product if we were able to consume all of the sodium in this reaction. Now that might be the answer to the question, but what I want to do here, the next step would be let's consume all the chlorine and see how much product we would get, and then compare and think about which one of those 2 amounts would be the correct answer. And so for chlorine, Cl2, 35.45 times 2, so that's about 70.90 grams per mole of Cl2. So we're just using the periodic table, 2 chlorine atoms to come up with the molar mass. But it's for every 1 mole of Cl2 that reacts with enough sodium to get there, we produce 2 moles of NaCl. So there's a lot going on in this step here, more than just that conversion. It's really saying when 1 mole of chlorine reacts with as much of the other reactant as it needs to react with, we get 2 moles of the product. And so then 1 mole of NaCl from the periodic table is just 58.45 grams. And this is going to be probably a quantity that's too much. So if I go 70.9, divide by 70.9 times 2 times 58.45, it's 116.9, call it 117 grams. Now, do you see, like sometimes if we're not thinking of what the problem really means, we may make a mistake and choose the amount that's greater. We want the amount that's less, because the amount that's less means when we hit 58.5 grams of product, we've run out of sodium. So we have no sodium left over. We don't have enough sodium to continue to get to the 117 grams. So it's like in this step here when we're saying if chlorine reacts with as much sodium as required to produce the product, we would get 2 moles of product. We can't get to the 2 moles of product because we've run out of the sodium. We run out of sodium when we hit 58.5 grams of product. So we're choosing the amount that's lesser. That becomes our maximum yield. Now, another way I could have thought to solve this problem, or maybe a way you guys had thought, did anybody just happen to sum the 2 masses up? I just think that that's probably the answer, 23 plus the 70.9. If you were thinking, this seems like a trick question, why would it not just be these 2 masses summed up together? The answer is, well, one of them could be left over as an excess reactant, not completely react. And so that's what happens here, is that the difference between those 2 masses summed up versus the product that forms must be the amount of chlorine that's remaining once this reaction takes place. So we have an excess reactant here, so this is left over after the reaction completes. We could have set up a BCA chart too. I know it's not your guys' favorite approach, but this math here actually isn't too bad, because it turns out you have 1 mole of sodium before the reaction and 2 moles of the chlorine. And then you can kind of see that, you have 1 mole of each of them. Just from converting 23 grams of sodium to moles is 1 mole. 70.9 grams of chlorine is the molar mass, so that's 1 mole of Cl2. And then if you think of your change here, the coefficient in front of the x is just based on the coefficient of the reaction, so minus 2x, minus 1x, and then plus 2x, and then the reactants are being lost, the products are being gained. And then the thought just becomes which of these, after the reaction completes, goes to 0. And then I think we can see pretty readily that if this goes to 0, then some Cl2 is left over. If the Cl2 goes to 0, we have negative quantities of sodium left over, which doesn't make sense. So we could go to the BCA chart too. So just make sure that you have a lot of understanding of these reactions, a lot of things and options to choose from. I think this is the fastest way. The way I went first is probably the fastest way to think through the problem, but a way to think through the problem is all you need on the test, as long as you can get through all the questions in the time you get for the midterm. Okay, so let's go back to this one reaction for just one more moment and look at the sodium and the chlorine, because this is actually an example of the next category reaction. We're going to talk about the oxidation reduction reaction. If I think about sodium, there's no charge on the sodium atoms in a block of sodium. Like, all the atoms are uncharged. If any of the atoms had a charge, then the entire chunk of sodium would have a charge. But it doesn't. Like, a block of sodium, a block of iron, if you have a pure element, the charge of the atoms are going to be equal to 0. So Cl2, the atoms are uncharged here as well. But when we're making sodium chloride, all of a sudden sodium picks up a charge, chlorine picks up a charge, and this is a consequence or the result of sodium losing an electron, and it loses the electron to the chlorine atom. So the chlorine atoms are picking up the electron to go to Cl-, so we're going from neutral to negative. The chlorine atoms are absorbing charge. And so we'll define this in a minute, but the act of losing charge or losing electrons is oxidation. So sodium is oxidized in the reaction, and then the chlorine atom in the reaction is said to be reduced. And then the act of oxidation means that it lost electrons, and then being reduced means it gained electrons. And so oxidation reduction we'll see is the tandem reaction where a substance can lose electrons and it can lose them to an atom that's capable of receiving them. So we're not creating or destroying electrons, we're just transferring them from one atom to another. We're just transferring them from one atom that has the capability of losing an electron to make a cation and donating them or giving them to an atom that's capable of receiving them to form an anion. Move back into chapter 4. Okay, so let's talk about how we have roles to assign. When I look at an atom and a molecule, what I want to be able to do is try to assign an oxidation number for the atom and the molecule. So if I have like KCl, it's like I already know the charges. If I have ions, it's just whatever the ionic charges are. So if I have KCl, then the atomic charges, the oxidation numbers are just exactly the charge on the ion. So atomic ions just have the oxidation numbers that's equal to their charge. So if you have like K2O, it's K still a plus, oxide's now a 2-. So charge oxidation number for atomic ions go hand in hand. So they're the same as each other. And so then how do we assign charge, though, becomes a question for things that are molecules. For example, molecules a lot of times don't have built-in charges. So when I'm looking at water, let's say, I want to be able to assign a charge for the H and the O in water, but I have to have kind of a process to understand, well, what do I set the charges at? And it turns out that the hydrogen is going to be positive as long as it pairs up with a non-metallic element, and then that's just going to make, to pair up with a +2, a -2 oxygen. But what we're saying here, though, is that for water, there's a big difference. Water doesn't really have these charges built in like NaCl does. So we're not saying water's ionic, we're just assigning it these oxidation numbers. And the oxidation number will help us later understand that water builds up the positive charge in the H and the negative charge in the O. Remember how we were talking about the hydrogen atoms will surround the negative charge like a chloride ion when it dissolves in water, and then the oxygen will dissolve or surround the positive charge. This just has to do with their built-in charges. So water doesn't really have these full charges, but the H atoms do end up being the more positive atom, and the O do end up being the more negative atoms when we look at something called polarity later that we'll see in chapter 8. So the rule for assigning oxidation numbers for oxygen goes that oxygen's oxidation number will be -2 with a couple of exceptions. And the exceptions will be whenever we have this peroxide ion, O2 with a 2- charge. There's a very rare ion that forms called the superoxide ion. The superoxide ion and even the peroxide ion, these only form in certain circumstances with alkali metals and sometimes with alkaline, and even rarely with alkaline. And so they're only going to form in cases where you know the metal's charge. For example, you could have a compound K2O2. When you're looking at this compound here, we know potassium has to have a charge of plus. There's 2 of them, so we know that we have to have a net -2 charge distributed across 2 O atoms. So do you see per oxygen, the oxidation number would be -1. And so this here would be potassium peroxide. And so this isn't potassium oxide, but this is potassium, if we were to name this, this would be potassium peroxide. So the peroxide atom, the O atom, has an oxidation number of -1, but we can deduce that in this formula because we get there from just knowing potassium has to be a plus. So what we're going to find for oxidation number rules is, as long as you know like a starting point, as long as you can look at a formula and start somewhere with a charge you know for sure, and an oxidation number you know for sure, you can usually start deducing the other atoms from there. Let's do an example of a superoxide would be, NaO2, right, the 2 as a subscript. And so for NaO2, sodium has a plus charge, so that's easy. The O2 2 minus is a collection of 2 atoms share a -1 charge, giving the oxidation number per O of -1/2. So the oxidation number of O in NaO2 is actually fractional, it's -1/2. So you'll see it's possible to have fractional oxidation numbers. That's okay, it's perfectly legal, and it just has to do with the net charge being shared by each O is -1/2. Now again, you're only going to form these compounds when you know that metal's charged, because they're only forming with alkali metals, which are always +1, or alkaline, which are +2. Now compounds with fluorine are an exception also for O, because we'll see the next rule here, or one of the rules down, is that fluorine's always -1 in compounds. So fluorine's always going to have a charge of -1. So let's look at fluorine. So F2, elemental form, that's 0. So when it's in its elemental form, any elemental form, the oxidation numbers are 0. So sodium, 0, Cl2, 0, F2, 0. But you put fluorine in a compound like Kf, well, that's easy, that's just negative. So plus and minus for each of them. So that's just the usual rules we've seen for atomic ions. But then if you have a compound that's maybe not all that common, but it's common in examples in this chapter, is a compound OF2. This actually does exist as a stable molecule. The fluorine just goes -1 by rule. So fluorine's -1 in all compounds without exception. And so -2 for the 2 fluorines, meaning oxygen goes to +2 to balance it out. So we're just balancing out the charge here so that the sum of the oxidation numbers sums up to the charge of the molecule. So molecules here, this is a neutral molecule, so the oxidation numbers have to sum up to 0. So this math here is how we're ultimately really making sure we assign the charges correctly. We're adjusting oxygen to positive to pair up with the 2 negative Fs. Now again, this is a molecular compound, so the atoms don't really develop these full charges, but they just, the prediction would be in the molecule OF2, oxygen bears the more positive charge, fluorine bears the more negative charge. So we talked about this rule already earlier, but 8 hydrogens +1 in molecular compounds, that means when it pairs up with non-metallic elements. And then it will be -1 though in ionic compounds. This is something we kind of saw back even in nomenclature when we were looking at classifying ion names and naming compounds like CaH2. So that's a calcium atom, just making sure we see that that's an A. So calcium has a 2+ charge. So I have a net 2- charge to distribute across the 2 H atoms, meaning each one of them is a -1. And that is the simple atomic ion of hydride. So the simple atomic ion of hydrogen in minus form is the hydride ion. So this is calcium hydride. And so hydrogen goes negative when it pairs up with metals because metals keep their positive charge. So hydrogen in ionic compounds is negative when it pairs up just by itself as an atomic ion with a metal atom. Okay, now all other atoms we're going to deduce from these conventions above, and then just by summing up the charges to equal the charge of the molecule or the ion. And so let's do a quick, now the next page has a bunch of examples, and a lot of them we already are looking at on this page to try to understand some of these rules, but let's think about KClO3. So KClO3, we could break down this way here first. We know that K+ is a positive ion. The collection of ClO3 bears a minus charge. Now, how do we break down the oxidation numbers? Well, the O rule is that the oxidation number is -2 with the exceptions of peroxides, superoxides, or compounds with fluorine. This is neither of those, right? So this is not any of those types of compounds, so oxygen has its ordinary oxidation number -2. Now, there's 6 of them, so I have, there's 3 oxygens times -2 is -6. And so if I look at the ClO3 minus ion, I have a -6 from the -2 charge times 3 oxygens. What does chlorine's charge have to be so that that ion has a -1 charge? So what do you guys think the charge of chlorine should be? Probably +5. So if I go +5 for chlorine, -6 goes to -1. And so for chlorate, if we have an atomic ion, then the charges should sum up to the ion's charge. If you then said, well, what if we go back to the compound? What if we go back to KClO3? It works out here too. Now, looking at this entire molecule, KClO3 is uncharged. So now +1, +5, -6 sums up to the charge of that molecule being neutral. So you can sum up all the atoms in one molecule or in the one formula unit that sums up to a neutral charge, or you could break the ion down independently by itself. We'll see a few more examples of this as we continue, but it's really just using the idea that the oxidation numbers collectively have to sum up to the charge. Now, one last thing I want to point out here is I'm writing my oxidation numbers per atom above and I'm doing the math below, just by convention so we keep straight the difference between the per atoms designation. So we're trying to determine per each of the atoms what's the oxidation number. I write that above. And then when I'm accounting for more than one of the atom and doing the math, I'm writing the math below. And so this is just doing the -2 times 3, etc. So I like to try to keep straight. Sometimes it gets confusing if you don't have a clear what's the per atom, maybe above the atoms, and then do some math if we need to below. Okay, so let's look at a bunch of examples here. So the first examples are just, elements in their pure form. Those are all uncharged, so that's very easy. So the atoms in an elemental sample, think of it this way. If one of the atoms had a charge, wouldn't all the atoms have to have the same charge? If they all had the same charge, wouldn't that element have to bear a charge? But the element's neutral. So all these elements here are neutral in charge, so all their atoms must be neutral in charge. So if we're looking at Br2, if the molecule's uncharged, then each of the atoms has to be uncharged. So hopefully the elemental form is easy. The atoms are uncharged in their elemental forms. And then when they pair up and make compounds, then we can look at maybe like Al2O3. We have two probably starting points we can think of the charges, because we actually know the charge of aluminum can only be +3. But let's say we forget that. Let's say we forget that aluminum is always a +3. Oxygen's a -2 with the exceptions of peroxides, superoxides. Those only form with like the sodium lithium group or the beryllium magnesium group, which aluminum's not in. So this can't be a peroxide or superoxide. And of course, this isn't a compound with fluorine. There's no F here. So that's not one of the exceptions of O. So I know there's a -6 collection of charge from the 3 O atoms. And then I have to have a +6 for the 2 aluminums. Per aluminum would be +3. So I could get to these charges. So the charges here and the oxidation numbers are hand in hand for ionic compounds. So as long as I know the charges for this compound, I know the oxidation numbers. So those are the oxidation numbers for Al2O3. Calcium nitride. Now again, maybe you forget this is calcium nitride, but we know calcium can only be a +2. There's a +6 here. There has to be a -6 across the 2 nitrogen atoms, meaning that's a -3 for each of the ends. N with a 3- charge is the simple atomic ion of nitrogen. Go 3 over, we get to that noble gas count of electrons. That's our ordinary nitrogen 3- nitride ion. Calcium sulfide, like calcium oxide, -2, +2 here, so pretty easy. We know calcium has to be a +2, sulfur has to be a -2. That's the ordinary sulfide ion. So that compound's name would be calcium sulfide. So hopefully name helps us understand the formula and the charges kind of all going hand in hand. Barium hydride. Barium's an alkaline metal, +2 charge. H has to be a -1 charge for each because barium's a metal. This is an ionic compound, so hydrogen with an atomic ion with another metal should go negative, and that pairs up +2, -2 for a neutral charge. O2F2 is kind of like OF2, another version of a compound with fluorine. Just remember the starting point here is fluorine has to be -1, like by rule. So fluorine stays negative. There's 2 of them. So I have to have a collection of a +2 charge across the 2 O's. And so per O, that's +1. So each O has a +1 oxidation number. The fluorine's a -1 oxidation number. And those are summing up to the neutral molecules charge. KO2, this is that superoxide example. So the minus here is for the O2. Let me write this over here. So the collection of the 2 O atoms has a -1 charge. And then per O, therefore, makes it -0.5 per each of the O's. Another thought is it's +1 -1 for the two O's, divide by 2, that's how we get the fractional minus half charge for the O2, the O atom in KO2. Calcium with O2, again, the thought is calcium's a +2, has to be a +2, that's the only charge possible for calcium. So we have a -2 charge distributed across two O's, that's -1 each, so that's calcium peroxide. So we see potassium superoxide and then calcium peroxide. Carbon dioxide. Now, carbon dioxide, you may look at this and say, is this a peroxide or superoxide? The key is that those are only forming, in rare cases with alkaline metals, you can form H2O2 for hydrogen peroxide, but that's the extent of it. Peroxide's a pretty uncommon compound. So let's just do H2O2 real quick. If we say this formula here, we know H has to be a plus in a molecular compound. And so 2 of them +2, -2 for the two O's, -1. That's how we can break this down and pretty easily see that that's hydrogen peroxide. Now, carbon dioxide, you almost see it in the name carbon dioxide. This is the oxide ion. This isn't a peroxide or superoxide. If it were, we probably would have called it carbon peroxide or something carbon superoxide. But it's carbon dioxide, -2 for the O's, -4, so a +4 for carbon. Now, carbon doesn't really bear a +4 charge in the molecule CO2, it's just the assigned oxidation number. So the prediction would be carbon should bear a positive charge in this molecule, the oxygen atoms in CO2. I'm kind of picturing in the structure, I know it's a linear molecule, you'll see that later, but I'm just picturing carbon has this positive charge, oxygen has a negative. Don't worry too much about what the delta means, that's the partial symbol. This just means that in the real molecule, when we get to this in chapter 8, we're gonna see carbon bears a partial charge that's positive, and then oxygen's that's negative, and that the signs of these charges are just related to these assigned charges from oxidation number rules. MnO2. Now again, manganese is not an alkaline or alkali metal, so this has to be the ordinary -2 oxygen, -4 overall, +4 for manganese. So this would be manganese 4 oxide, not manganese 2 peroxide or manganese superoxide. So you don't have to worry about peroxide or superoxides because they're only forming when you know the metal ion's charge or the H atom's charge. Now what about copper with the perchlorate ion? And so copper here, or like probably the actual starting point is that ClO4 is a minus charged ion. If we forget that, we're gonna kind of probably not know how to get copper's charge. So -2 here, that's how we determine this is a copper +2. So the name here would be copper 2 perchlorate from nomenclature. And then if we're breaking down the Cl and the O atoms in ClO4, we have two options. I can either break it down in the full formula, which is actually, I think, a little trickier, or we could just look at one ClO4 minus ion and then work out the charges that the atoms have to sum up to -1. And so to sum up to -1, I have a -8 coming from the 4 oxygen atoms being -2 each. So chlorine has to be +7. You can get there in the full formula, but if you do the full formula, I don't know if this will confuse or make things make sense, but copper's a +2. I have 8 oxygen atoms, 4 times 2 oxygen atoms that are -2 each. So -2 times 8 is 16. And this is all going to sum to 0. So then what's the chlorine atoms in the middle? The chlorine atoms in the middle have to be +14. And there's 2 of them. Gets us to +7. So you can do the math on the full formula. It just has more parts to it and a little bit more thinking goes into it. We just have to do 2 times the -2 for O times the 8 O atoms, and that's -16. We get a +2 from the +2 copper, and then that gives us a 14 for the 2 chlorine. So we get the same math and the same answer emerge, but I think it's a little simpler if you just break ions down into one ion at a time. Now, chlorine F3, I don't think it was on the page, I don't think I mentioned this, that fluorine's always -1. And so anything that fluorine forms a compound with has to adjust accordingly. So the other halogens will go positive like oxygen went positive in compounds with F. So -1 for fluorine, -3 for the 3 Fs, so a +3 for chlorine. And then carbon tetrachloride from nomenclature. This is a binary molecular compound. So carbon tetrachloride, -1 for the chlorine. So halogens are -1, except for when they pair up with O or F. And so our halogens -1, so -4, so that's a +4 charge for carbon. And let's do one more example here. Let's do K2Cr2O7. This is actually a fairly commonly used compound in the lab. This is potassium dichromate. You don't have to know it for any nomenclature unit, but the two potassiums are +2, meaning this CrO2O7 collection has a -2 charge overall. So we have a -2 for O. There's 7 of them for -14. And so then our two chromiums have to be +12 for this to overall equal 0. You could break down CrO2O7 to separately 2 and get the same math. So +12 minus 14 equals -2. Or altogether here, +12 for the two chromiums. So that's a chromium with a +6 oxidation number. Okay, so let's look at a couple more. Well, let's look at a couple examples of reactions. I think there's a couple questions on identifying oxidation numbers. And so then the oxidation reduction reaction is where you have the exchange of charge taking place within a reaction. So an oxidation reduction reaction is where, if you look at the reactants versus the products, you can see a change in charge. So like H2 plus O2 goes to water is an example of an oxidation reduction reaction. And then which atom is oxidized, which one is reduced? The O atom is picking up the electrons, it's accepting the electrons that hydrogen is losing. So hydrogen's losing electrons, so the H atom is oxidized. And then the O atom in this reaction is reduced. I gain the electrons. So losing electrons is oxidation, gaining electrons is reduction. So some of the lingos, just to make sure we remember which is which, like the two words or phrases I see people remember a lot is either Leo, the lion goes grr, for losing electrons is oxidation. You might remember oil rig for oxidation is losing electrons. Rig, reduction, is gaining electrons. So just, either remember Leo the lion goes grr or oil rig, or a couple of words just to help us remember which one is the losing electrons, that's oxidation. The active gaining electrons is the reduction step. And they have to take place tandemly. So if a reaction is going to be oxidation reduction, one atom has to accept the electrons lost by the other. So we have to have these two reactions occurring tandemly in a chemical reaction for it to be an oxidation reduction reaction. And so then what I'm doing here is I'm looking at the atoms in the reactants and trying to determine from the reactants to the products, do the atoms gain or lose electrons? So it's always the thought, does the H atom in the reactant side, does it gain electrons or lose does it gain electrons or lose electrons as the reaction occurs? We have a neutral H atom going to plus. So that's hydrogen with one electron, losing an electron. And then we have oxygen that's neutral going to negative charge, that's picking up electrons. So you can kind of go back to, chapter 1 to say if you had H neutral, how many electrons? 1 electron. If you had H plus, how many electrons? 0 electrons. If you had oxygen, how many electrons? 8 electrons for a neutral oxygen. If you had an oxygen with a 2- charge, we picked up 2 electrons for 10 electrons. So just in case we've had that loss of what does it mean to count electrons from like chapter 2, it's just counting up those subatomic particles on the electron side. So you get the negative charges adding electrons, you get the positive charges having lost electrons. So lead reacting with nitric acid, lead neutral, nitric acid plus minus. We get lead 2 plus nitrate ion, neutral hydrogen forms during the course of this reaction. So this is lead ionizing in acidic solution to form hydrogen gas that bubbles away. Gas bubbles away, this reaction takes place readily in solution. Now this reaction here is actually a very important reaction. This is how lead leaches out of lead plumbing. So if you use lead in plumbing and you have corrosive water, that just means water that's of relative high acidity. If you have acidic water flow through plumbing with lead in it, what's going to happen is lead's going to leach out of the water and form lead ions in the water. This is the primary way that lead ion forms in plumbing purposes or in situations. So you shouldn't use lead in plumbing. And unfortunately, we did use lead in a lot of plumbing that needs to be removed if it hasn't already. And so that's where most of the lead in drinking water comes from, is just lead being used at some point along the plumbing process. Now let's look at a metathesis reaction real quick. So a metathesis exchange reaction, remember that's the reaction where we're just exchanging the metal ions. Do we get a precipitate? We do. We form AgCl solid, precipitates here in KNO3. But do you see here that this is not an oxidation reduction reaction? So we didn't change the charge state of anything. So an oxidation reduction reaction has to take the charge of like lead and has to change it to 2+. That's lead losing electrons. So in the lead reaction, lead is oxidized. And then the H atom is reduced because it's the atom that's going from a plus to 0 oxidation number. And then the nitrates say the same for the lead nitrate. But in the AgNO3 example, there's no exchange of charge taking place. So there's no difference of charge. So that's not an example of an oxidation reduction reaction. So I'd like to point out that our acid-base reactions also are not oxidation reduction reactions. So when you look at HCl plus KOH forming NaCl plus water, nothing actually changed there either. So in our first half of the chapter, those reactions we were looking at, those were not examples of oxidation reduction reactions. So this is kind of a new reaction here for our chapter 4. Now, it turns out different metals have a different range or reactivity trend in solution. And so the most reactive metals are at the top. That's our alkali metals. And alkaline metals, they're going to be the ones that are most readily forming cations in solution. And then if you look at the bottom of the chart, these are the less reactive metals. So less reactive metals at the top, more reactive metals at the top. There's actually one non-metal here, hydrogen, kind of towards the bottom. But everything's metallic here except for the hydrogen reaction. And so the less reactive metals at the bottom. And then these are the metals that we make coins out of. So we make coins out of the more stable metals because they're not going to dissolve in water. They're not going to dissolve in acidic solution. And so if we're going to make plumbing, we should make plumbing out of copper, not lead, because lead is more reactive than hydrogen. So we can use this activity series to help us predict when reactions take place. We'll see an example of this in the next slide. But if you took like magnesium, and if you put it into a solution of any of the metal cations below, then the metal cations below are going to reform that more stable metal, and then the more reactive metal is going to form its charge state. So if you take a metal at the top of the chart with a cation below it, then you'll have the reactions take place to ionize the top metal and then go back to the metallic form on the bottom. Let's look at this slide here that kind of goes through that query or that thought of, well, which of the reactions is it that will take place? If I take copper, can copper dissolve in zinc, or will zinc dissolve in copper solution? So let's take an inspection of where copper is. So copper's here, and then zinc is here in our activity series. And so zinc is more active, it's more reactive. Zinc has a higher reactivity. It's more likely to react in solution than copper is. So if I take zinc as a metal into the copper solution, then what should happen is that copper should reform copper, and then the zinc should dissolve. And so copper into zinc, so copper solid plus zinc sulfate, that I should be able to get copper to form solid plus zinc, I should be able to get zinc to, let me write, so we're thinking, does copper dissolve in the zinc solution? Let me write the second reaction. Let me write the reaction as zinc. Will zinc react in the copper solution? So zinc into copper, that's what I was just thinking. That's what I was just writing out, is that zinc solid into the copper solution should form copper solid, and then the zinc should dissolve. So this reaction should be the one that takes place, that will form copper solid, and then plus ZnSO4. So we're just having a simple exchange of electrons. We're taking 2 electrons from the zinc and putting them on copper, so copper goes to 0, and zinc goes to 2+. And so we're oxidizing the zinc, we're reducing the copper, and we're doing so because the activity series says zinc is more reactive. So zinc, if this is more reactive than the product we're producing, think of how it's always going to be better in the lab to take the more reactive thing to produce the less reactive thing. And so this is the reaction that we would predict would take place in solution. And then the opposite reaction, where if you imagine taking the copper, will it dissolve in the zinc solution? Well, if it did, we'd get zinc solid and then plus copper sulfate. And then we can think, well, why would we start with something less reactive and produce something more reactive? That doesn't make fundamental sense. So we shouldn't be able to take something that's less reactive and produce something that's more reactive as a result. And so that reaction should not occur, and we should not get these products, and we should see that this reaction of copper into zinc would be a no reaction. So let's do a quick little demo here of trying to see the difference of putting copper into a zinc solution and zinc into a copper solution, and just see if our prediction works out. And so the copper solution is the blue solution, and we know that this is the copper. So I'm going to put the zinc through the copper, this should react. Look how quick that reacts. Like, you see the brown copper atoms forming on the zinc surface, so that reacts readily. And so then as the copper dissolves in the zinc solution, and nothing happens. It looks exactly like it did before. So no change here, so no reaction of the copper into the zinc, and we get the copper forming into the zinc solution. One last thought, can we look at gold? Gold down at the bottom of the chart. Gold is really stable in the sense that it's at the very bottom. It's not reactive in almost any kind of solution. H plus is the solution that moves up to H2. So let's do a test here. Who thinks my gold is going to dissolve in the HCl? Now, H2's here, gold's here. Gold is less reactive. As long as I'm not wrong, this should not dissolve in acid. This is HCl, 1 molar, 1 mole per liter HCl. Thankfully, it didn't dissolve, so I don't have to explain my wedding ring at work today. So my gold ring did not dissolve, and it's all about relative reactivity. Okay, so the issue here is if you're thinking gold into H plus, will H plus return to H2? No, because gold is not reactive enough. What I want to do to get acid to react is I want to take a metal solution above hydrogen on the chart. If I were to take zinc into acid solution, zinc would react. So let's actually do that test real quick. So if I flip this over, can I get the zinc to react into the acid? Maybe it's not so fast. I should have safety acid for this. May not have enough concentration to see it, but if we sit here long enough, I bet we would see that zinc dissolving. Because what we need is, for acid, we want to have a metal above it, then H plus returns to H2, and then that metal ion reacts into its cation form. So we can use the activity series to predict when oxidation reduction reactions take place. It's for the metals that are more reactive, reacting with the solutions of the cations below them on the chart. We'll see some more examples of this into Wednesday's lecture. We'll move into the molarity unit, concentration unit as well. Have a great day, guys.